All right, hello class. We are going to do some real quick notes on forces in two dimensions. Hopefully the volume's not too loud. This camera's a little weird, so as is this entire process. So hopefully this isn't too weird for you guys. But just wanted to do some explanations about some more complicated aspects about two-dimensional forces. Okay, we know that force is, of course, a vector, okay, which means it has magnitude as well as the direction, okay? We can indicate that with an arrow. Now, up to this point, we've learned, you have an object getting slid across the floor, say, and you got one force pulling this way, and you got another force pulling this way. Say this is maybe 100 newtons, this is maybe 70 in the opposite direction, so it's negative 70. And say you have its weight, it's 900 newtons, it's not accelerating up or down. That means that the normal force is 900 newtons going up. Now, this, which is a problem type that we've already done, is also two dimensions, but the vertical dimension winds up canceling each other out because you have 900 newtons going up, canceling out the 900 newtons going down. So really the only thing we had to deal with were these two forces, these horizontal forces. And in this case, the net force was 30 to the right. And if we knew what the mass of this block was, and I guess we do because I gave you the weight, we could then figure out the acceleration because that would just be the net force divided by its mass. But what about when all the forces don't cancel out? Or what about when you have forces that act at some angle? So there's two different kinds of situations that we need to talk about. So the first one is a force at an angle. So now let's consider we again have a block on the ground. For simplicity, so even though that line doesn't look horizontal, we'll say it's a horizontal ground. For simplicity, we'll say that force of kinetic friction is 0. Frictionless surface. Won't of course always be that way. But let's say we are pulling an object, like with a rope or something like this, that's at some angle. We'll say that that angle is 30 degrees, and we'll say we're pulling with a 100 Newton force. And let's just say that the object has a mass of 5 kilograms. Okay, so there's no friction, there's no opposing force. Now, in this case, this force is at an angle. And we know that when we have a force at an angle, that means that we need to find components. So this force is both pulling upwards as well as horizontally. Okay? So it's pulling this way as well as this way. But only one of those forces is contributing to any kind of acceleration. Okay, this vertical force is now kind of teamed up with the normal force to cancel out the gravity. But if the block is accelerating horizontally, that means that only the horizontal component of this force, we'll call that Fx, is causing any kind of acceleration. So if we know that there's a horizontal acceleration, we need only to consider horizontal forces. There is, of course, a Fy here, but the Fy, the weight going down, and the normal force going up, the normal force is actually reduced now because of the vertical force, but this, and this all cancel each other out. So for this simple problem, we don't really need to worry about those quite yet. We have a horizontal acceleration that was kind of part of the problem, so we need only to worry about the horizontal force. So one way of looking at it is just like we had Newton's second law where he said net force is equal to mass times acceleration. That's true in both dimensions, the horizontal as well as the vertical. Now, in this particular problem, there is no vertical acceleration, so that's 0, which means that's 0, and we don't need to worry about it. But this guy, the net horizontal force, is equal to mass times the horizontal acceleration. Now, in this very simplified example, there is only one horizontal force. That is the x component of the applied force. If there is friction, which there often is, there would also be friction. So how do you find Fx? How do you find the horizontal component of this force? The same way we always find it, using trig. And if you remember how to find an x component of a vector, that's going to be that vector times cosine of the angle it makes with the horizontal. And that's the same true here. Now, we only have that one force, as you can see up here. So this is the net force, and so you could set that equal to mass times the horizontal acceleration. So, say I want to find what the horizontal acceleration was. I didn't give you that. I gave you the mass, and I gave you what the force is. So if we solve this equation for the horizontal acceleration, it becomes horizontal acceleration is equal to F cosine of theta divided by mass. Now we plug all that in. F cosine of theta, that's the horizontal component of the vertical force. Plug that in. Sorry, comes out to 86. I'm just going to rewrite this down here. 86.6 newtons is on the top, and the mass which was given to you is 5 kilograms. And you can really quick punch in 86.6 divided by 6. Divided by 5. And you get an acceleration of about 17.3 meters per second squared. Now, that seems high, and it is. That's because you have a force with nothing acting against it. Okay, you have a relatively light object, a big force, no friction or anything else opposing it, so we have a kind of a high acceleration there. Okay.